But it's okay. Now, so the D, remember the other one I use or DSP. Is that okay? So I'm going to call this density. And I'm going to call it maybe D norm D. Okay, so D norm dense. So that at least it gives you an indication. What is X? This X is what? It's the insurance claim. This is the data. So I come back and take the data, then I'm going to compute the density, of course, with what? With the parameters estimate I got from that data. So I'll call this one, the first, remember is, the first one is the mean, isn't it? Yes, so I call mean will not be 0 here, but what? The first one. What will be standard deviation? The second one. Are you following? Yeah. Please. In Ghana, we say miaweni.
You are right.
No, this one you can't weep. Just look at us. Okay, you'll be fine. So these are the densities. So if I have the densities, what do I do now? I need to combine them, right? So that I can sort each data with its corresponding what? Density. Okay. So I can go back then and copy that data frame with it, like this. So when you go home to your residence and then you check, you realize that everything is just the same. If it is not, let me know. So the density is going to be what? D norm dense. Then now I can sort it. Here I can just line it on what we did, and you will see that this will also be distorted because it is not what? It is not sorted or arranged. But let's see. So this is the claims. Y is what? The density. What color should we give this? We already had red. 5. Okay, so let's see. So you see what is happening. So this one, the top is the normal distribution. You see, it's not capturing the upper part. So this is what I want you to understand. The programming, it's just the typing. The prince is the same thing. Nothing really is different. So let me get my histogram done again, and then I fit the. It doesn't matter which one I fit. They were all the same, like that. And then now I can go and organize this. That one, right? Okay. Once I organize it, I can. So we are sorting this. We replace that one with that. Yes. And oh, I did not change the name. Okay. I did not change it, so. But this one I did not. Okay. You people. Okay, so which color do you want? We said 5, right? Yes. So now let's see. Okay. So you see our plot. Now the question is, which one would you prefer? Green. Please, do you get what is going on? So this is how we assess the fit of a data to a particular distribution. And remember, in the normal, I use the maximum likelihood. I could have also used what? A method of moment. There we will see some slight changes because the variance the estimators are different. It differs by 1. The numerator differs by 1. So in that case, if you have a large data set, the difference is not felt much. Because 2,000 and 1,999, if you divide 1 by that, you tend to get almost the same thing. But if you have 9 and 10, it will be a bit profound. Like that. So that's the sort of thing I want you to be able to do. And the superimposition, you need to get your plot, you need to get what? Line. You can also use point. If it is point, it's going to just give you dots around that. So that's it with this. The last thing I wanted us to do is to actually assess whether the method of moment is better than the maximum likelihood. We could have done this by taking a smaller sample size, a medium, and a large, and taking very large one. But unfortunately, we don't have time. But I have a video on it that I can show you. Send to you. Yes.
The default density plot.
Yes.
The distribution is using.
The default.
Yes.
Which one?
The normal density plot. You can just plot density.
Yeah, that one use a kernel.
Use
a kernel density estimation.
kernel.
Kernel, like this kernel density. It's like a non-parametric. So it uses kernel density. So if you do a plot density, it will fit. Yeah, that's an empirical one. That's a non-parametric. So I think this is a good time. So as I said, I couldn't achieve my last topic that I wanted to check. How to compute bias and mean square error. Yes. On the mean square error. This one. Yeah, if you are doing simulation to compare estimators, then you need what? But I have a video on it. I'll send you. What really happens? I can show you the concept. Now, assuming, let me show you the concept. What we use in statistics. Now we've discussed method of moment and if I show you, you will be able to implement it on your own. But I'll send you a video of it. So maximum MLE for the normal distribution, sigma squared is what? 1 over n sigma x minus x bar squared. Right? Then S squared is what? 1 over n minus 1 sigma x minus x bar whole squared. I want to really check which one is the best. In basic statistics, statistical inference, you do this. We can actually find the variance of this, even though it's variance, we can find it, you know that. Good. Then I can also find the expected value of that one. We can do so because we know the distribution, right? Similarly, I can find the variance of sigma cap squared and also the expected value of sigma cap squared. We are not interested in this because in this case you can find an explicit expression for it. Okay, but I can use simulation to do the same thing. What am I going to do? Simple. I'm going to simulate observation from a normal distribution in which I know the variance. So for example, I simulate observation from a normal distribution with mean for variance, let's say 10, or let me say 9. If the variance is 9, then the standard deviation is what? 3. Is that okay? Good. Each time I simulate the first one, I find this. When I find this, I expect it to be 3, but it will not be 3. Okay? It may not be 3. Then I do this one as well. And I can do this over and over and over and over and over like 1,000 times. So if I am using this one, I simulate the first observation. This is so you can create like a data frame. You have sample, then you have sigma cap squared and what? S squared. So sample 1, maybe this one is 2.99, this one is 2.98. Sample 2, this one is 3.20, this one is 3.01. And so forth and so forth till we get to what? Maybe 2.87, this one 2.98, something like that. Do you know what I'm saying? Yeah. So each time I simulate observation, I find what? I use my estimator to, just like we did for the mean, the inverse of the mean. Right? Now if I do this, it means that I have R of this, R of that one. So how do I compute this expectation? I'll find the mean of this. I expect it to be equal to what? 3. So my bias, which we find as the expected value of what? Theta minus theta would then be equal to the mean of this minus 3. Okay? And then my MSE would then be equal to 1 over R. Remember, is the square deviation of this. So I take each theta I subtract 3 from it, and I square it. So that's my MSE. I expect this MSE to be closer to 0 as n increases. We call that in statistics what? As n increases, I expect my MSE to be close to 0. If the estimator does that, what do we say? It is. Hey, man. Yeah, not at the Catholic Church. Speak up. If that happens, what do you say? It is consistent. Consistency, that's the principle of consistency. As the sample size increases, we expect to get closer to the parameter. Of course, if this one is closer to 0, then it means the parameter, the statistics is close to the parameter. That's it. That's the concept we use. So it's not that difficult. This is the concept you use in assessing estimators. So when I finish, I want the bias to be close to 0. I also want the MSE to be close to 0. The estimator that gives me that will be adjudged the best estimator. That's the sort of simulations we do now to assess estimators. Any question? As I said, I will send you a video on this that you can actually implement some of them on your own. Yes. Areas. Do you want me to show you some areas in Ghana? What is this area? No, I mean, you said area. I thought you were coming to tell me this area. Area in statistics. On Friday. Okay, so basically, is everybody okay with what we have done? This week. After all the questions you've asked. Then you should have told me that, said this one, don't worry. After asking all the questions, this one, You are worried about hypothesis testing. But today I have explained all that. And you still have issues. Which one?
All of them.
Every. In the morning you did not say to say that. Okay, so what do I expect from you? Well, I have not even said the question. So. There will be no surprises. That one I can guarantee you.
You store packages.
Yes, you install a package. You see. Okay, so usually what I do is this, that I'll give you a data set. It may be a data set that is in R, or I may get a data set on my own and send it to you maybe through email or put it on your drive and then you access it. Which means you should be able to read the data from either a package or in, let's say, an Excel or text format into R. That's one. You should be able to check, so now you know the areas. Yes. And you were asking La Paz or okay. Now, once you're able to read the data, you should be able to describe a data set. And you've done so in your assignment. So what is it? Now, I will test whether you can describe a data using descriptive statistics. Which means I may not point you to that, use a pie chart, days, that, but I'll say use appropriate. I want you to be free, okay, to describe a data set in your own way. All right. So descriptive, if let's say I give you two data sets and I say describe it, then I want you to be able to describe the first one, the second one, and also compare. Did you get it? So if I'm marking, I'm checking all these, whether you have done each of them. And we've done some like using box plot. You can plot a histogram and so forth. But usually the box plot is better because it gives you what? Side by side and you can compare them.
Yes, please.
We can also use what? Descriptive statistics in terms of the numerical one. Plot them. I think yesterday we saw some with describe by and so forth. Together, and then you can now walk through it all to describe. So basically, I want that part. You should be able to do that part. Second, you should be able to do hypothesis testing. That reminds me, my last assignment. So we'll send it to you today.
Assignment.
After weekend. You don't look happy at all. Yeah, we are always happy. SCC, you don't buy anything on your own. You must be laughing. So, hypothesis testing. You should be able to check out, ask you something on two categorical variables that you need to be able to compare to see whether they are dependent or not. I'll ask you one on correlation. So in correlation you have to plot, describe it, and then test, alright, to make a conclusion. I may ask you one on single variable. That is a t-test on single variable or two variables, whether independent or dependent like we have done. Analysis of variance. So, how to tell the and what is this today? I do trust you. I know you won't disappoint me. Okay, so, yeah, so, I want to do something on what we did today. So, I'll give you the script now. So, at least you've seen normal. Go to the faith-based app. So I won't let you do, let's say, method of movement for parental and all these things. But I'll give you a data set. Okay? Then I want you to plot this data. Okay? And then choose which distribution fits it well. If you are checking that, you see this part is not important. This part too is very important. Is that okay? Alright, okay. One more thing. Now, I am torn between something. Now, how would you, if I give you a value here, how can you tell me the proportion of observations above this? I can go to the price data. Claim. So, what is the proportion of claims over 300?
We check over 300, then we over the entire total.
Yeah, that's it. Is that all right?
Try to put a bit.
For him. I'm like, okay. Okay, but we talked about logicals, right? So, all you have to do, if X is a claim, X greater than what? 300. This will give you what results? True, false, and so forth. The sum of it will give you what? Sum of this. Because true is 1, false is 0. So the sum will give you what? Number of what? Which is? Yes. It will give you how many observations are greater than what? 300. Is that okay? Please, is everybody okay with it? Yes. So if you divide by, let's say, length of what? X, what would you get? The proportion. If you multiply by 100, what do you get? Is that okay? Is that okay? Okay. Now, you know survival function. But you know CDF, F.
Yes,
You are being, no, but these are just, what do I call it? I want a word for it, but it's not coming. No, I don't need to teach you this to ask you. Maybe that phrase will be better. Okay, but I mean, it's just implication of what we are doing. It says, okay, now, so the proportion of those of observations greater than 300, we can get it through this. You know that you can still use your P as well to get this. Because we said that P is what? For the density function, sorry, the cumulative function. Okay, so this one, what we have done, if this is here, over here, that is the survival function. What about up to here? F of S. All survival. Don't worry, well, you survive. Okay. So f of x is from negative infinity to what? A certain point. What about the survivor? From a point to what? That's what we have done over here. Yes. So, if I have any distribution, I can check this, the sum of these divided by the length using, let's say, the PS or P norm or those and so forth. So check through that as well. How to find the proportion above a certain point. Empirically. So this is the empirical distribution, and I can also find the theoretical probability. You are lost. You were not listening. But what is the probability that you get a claim over 300? How are you going to solve that? Total, yes, over the total, that's it. Okay. Now, you can also, once you have fitted this distribution, you can calculate it from that distribution. That's what I was explaining. Every distribution, once you do DS, there's what? PS. The P is what? The F. The cumulative distribution. So 1 minus the cumulative distribution function gives you what? The survivor. Yeah, so if I have done exponential and I want to check how the exponential fits the tail, I can do PS. Okay, PSP. Okay, then X will be equal to 300. I think there's a lower dot tail or something. You can check. Question mark. Yes. It's Q, right? Okay. So that's a quantile. So Q. The representation is Q. And then you have what again? Rate. What? Rate, yeah. So the rate is what we computed. 0.00, and then what again? Does it have lower dot tail is false?
True. That's true.
Yes, it's true is for because the true is F, false is the complement. Hey, take your time. It's time. Look at this. These are all, this is what I'm trying to show. So AB line is horizontal or vertical line. So I want a vertical line at 300. My friend, I said as for a programming language, nobody will be able to teach you everything. So you learn, you embrace things. I keep on learning. You are so fixated with tests, but your interest will be on what we are doing. Yeah. As for the test, I can even give you the questions. Because you come and do it anyway. This is not something that you need to write it over there. So just embrace whatever that's learning, but you don't learn for only exams. But that's what I'm teaching you. That's what I'm teaching you, and all what we are doing is just implication of what we have done. There are levels of questions you set. It's not okay. It's okay. Don't let it. You see, what we are doing is proportion of, you answered this question, proportion over 300, right? What I'm telling you is that what you find from the data is what the data is telling you empirically. But if you have fitted the distribution, how do you check whether you are an insurance company, right? If you have claims over here, they are so huge, it can collapse the company. So if you have a distribution and it fits here perfectly, and it is unable to fit over here, you are in danger. Because you can't afford to cater for these people, these claims over here. So sometimes you tend to look for distribution that will help you to model the unexpected ones than even the expected ones. And that's the principle I'm teaching you here. You know it. It's just that, I need to emphasize it so that you know that this has applications in our everyday life. So, I fit a normal distribution. You see, the normal distribution is not good, this area. But we can check here to see it may even perform better than the exponential. So, if I'm at the company and I'm the risk manager, I'll be assessing all this. Okay? Those that are expected, those that are unexpected, which one is doing better? How do you check it? That's what I'm saying. You know the proportion from your previous year's data. You fitted the distribution. How do you check whether this one fits the table? Calculate the proportion that it is telling you are beyond this. Then the density we just fitted, you can also calculate the proportion. The closer it is to it, the better. That's all I want to put across. And as for this, you know that you can use this sum and so forth to find it. But what about that from your distribution? We've used density, we've used R norm, and also the next one also the P. And it's over there. If you take any of them, so if you go to P here, it shows over here. Q, we've used that one to calculate the test statistics. What we have not done is a P, and I'm saying that it computes the cumulative distribution as well as what? The survival function. The cumulative is from negative infinities, that's why they say lower the tail is true. So it calculates from the lower tail up to what? A point. And if you say false, it will calculate from what? A point to what? The upper tail. So here we are looking at the upper tail. So you put lower the tail to be what? False. Okay. Whatever you put there. So for example, if I take this, do you remember the value of the kill? This. Can somebody provide us with the empirical proportion? So this is true. Rate was what? 20 what? 311. It's okay. Then the kill is 300. So this will give me the, sorry, this should be false, right? But I can also do 1 minus when it is true. Okay, so this is the proportion of observations greater than what? 300. Is everybody okay with this? I can get the empirical one, what the data is showing. What you are doing is that, are you able to capture the probability beyond that? So if you have that as, let's say if you are in a reinsurance company, or you may be interested in it, or you're a risk manager, you are interested in this kind of things. So I can look for insurance claims greater than 300. This should give me true or false. You get it? True, all those greater than 300, rather, sorry. 300. So all those greater than 300, I'll get through. Those less than that. So you see, it's only one, right? Only one out of 64. Is that okay? So it means that the sum will give me what? 1. Is everybody okay? I can divide by what? The length. Sorry. Length of what? All this. We know it's 64, but we can just do it like this. So this is going to give me the proportion. 0.01. What is the distribution giving us? What did they give us? I can do it again. Okay. So it means I can also do that for the normal by using what? P norm. Then my K will be also that, and then I check that. So in simulation, you can actually do this. And these are some of the things you may be interested in later on. This is my research area in statistics of extremes. Very important in predicting rare events. And it can be either on the right or on the left-hand side of the distribution. So please take note, there are so many applications in so many fields. In climate studies, what have you, hydrology, yeah. So, okay, yes. Yes.
How would I conclude that the distribution is 50%?
Yeah, it must give you the probability that is close to what is actually happening. So the top one, 0.156, it means that 1.5% or 1.6%, that's the probability. Okay? This one is giving us what? 0.2. So there's a shortfall. It is telling you that it is very rare, but actually it happens if you take 100 observations. It's likely that 2 will be beyond. That's what that means. If we take 100 observations, it's likely that 2 will be beyond what? 300. But what your model is telling you is that if you take 100, almost 0, you will not even record 300. So you will be there. Go ahead and invest all your money in, and then there is a claim over that and you can't pay. The company will be bankrupt. Because the customers will now start agitating. They don't pay claims and so forth, and then you are gone. As soon as they say it on radio, that's it. The company is gone. So you want a distribution that will give you better. And if we go and do for Pareto and so forth, you realize I will get one that is closer to it. So that's the sort of thing. Some of you may take it as your thesis later on. Yes. Okay, so I think that will bring us to the end of the class. It's been nice having you. Yeah, the time is indeed short. But we've done, I think you have the basis now to build upon it. You are interested in statistics, better. Okay. As for statistics, we eat in everybody's backyard. From accounting to geology, you find statistics in there. Yes, we have so many. We've done just a tip of the iceberg. So we haven't really gone anywhere. Okay, so I wish you the best for tomorrow. I'll come around, but I'll leave you. So that you oh, you can ask. We will be here to help you. Yeah, so. Previous? Yeah, I'll send it to you. Chantel will send it to you. Will I? Ethiopia. Tomorrow we'll go to Addis, eh? Yes. Open book. Do you have a book on this one? Do you have some books? Okay, you bring it. You just have to do it on your own. That's all we require of you. A moment. Let me send this before, because when I leave here,